From Geometry to Calculus, A Brief History of Integral Calculus by Aaron, Cynthia, and Joyce.
Perhaps you have heard that Newton was one of the people who invented calculus. However, when Newton was in college, he actually got introduced to the concepts of basic calculus as we know it from a series of lectures on geometry. Why was calculus considered part of geometry back then? To find out the answer, we need to backtrack in history to ancient Greece.
2,000 plus years ago, without the tool of modern calculus, people had no way of finding the area of curvy shapes like the circle. Yet mathematicians were deeply drawn to this topic since approximating the area of these shapes, the circle in particular, had many useful applications. A lot of different ways were developed to do this approximation. Among them was the method of exhaustion, used by the great Greek thinker Archimedes, around 200 BC, which became a big stepping stone on the pathway to calculus.
Here's what Archimedes started off doing. He inscribed the square inside the circle, then circumscribed another square outside the circle. He calculated the areas of the squares which correspond to the lower and upper bounds of the circle's area. Then he found their difference, which equals the range of error in his approximation. If he keeps increasing the number of sides, n, the difference in area between the inscribed polygon and the circumscribed polygon will become really small as n becomes large. By using the two polygons with 196 sides, Archimedes eventually approximated the value of pi, the ratio between the circle's area and its radius squared, to be between 3 and 10 over 71, and 3 and 1 over 7, which are 3.1408 and 3.1429 in decimal form, which has an error of approximately 0.001.
So how is all this related to calculus? This vaguely referred at the concept of infinity and infinitesimals, in other words, infinitely small, which was quite a bit of a taboo topic amongst mathematicians at the time. Archimedes' work inspired other mathematicians to further explore these concepts. In particular, it led Italian mathematician Bonaventura Cavalieri to develop the method of indivisibles.
In this method, Cavalieri regarded lines as made up of an infinite number of points, areas as made up of lines of infinitely small thickness, and volumes as made up of planes of infinitely small depth. Then he could calculate whatever quantity of the higher dimension figure by summing its elements in a lower dimension. For example, if two solids of equal height are cut by parallel planes such that each pair of areas matches, then the two solids have the same volume. We can use a stack of coins to better illustrate this theory. Each coin can represent a plane of infinitely small depth, and since the area of each coin in stack A matches a corresponding coin in stack B, these two solids have the same volume despite having different shapes. Doesn't this remind you a lot of integral calculus?
Based on the work of numerous mathematicians, including the ones we talked about previously, a British math professor at Cambridge, Isaac Barrow, came very close to developing the fundamental theorem of calculus. Barrow used geometry to find that an inverse relationship exists between integration and differentiation, although he did not establish it concretely in a theorem. In modern terms, he basically came up with this part of the FTC. His proof gets quite complicated, and it's hard to summarize here, but you can find more detailed explanations on his proof at this link. However, the story didn't end there. Barrow taught the basic concepts of calculus in a series of lectures on geometry, and among the people who attended his lectures was Isaac Newton, who perfected Barrow's ideas on the relationship between integration and differentiation. In addition, he established a method of finding derivatives in a mathematically rigorous way for any function.
He proved that as the distance between points A and points B1, B2, and B3 continues to decrease, the approximation of the slope of the curve at point A becomes more and more exact. Using this new concept of derivative and the relationship between antiderivatives and integrals, Newton was able to come up with the calculus that we know today, starting with the fundamental theorem of calculus.
Here's a quick recap on the fundamental theorem of calculus. The formal definition of the fundamental theorem of calculus is as follows. 1. One of the antiderivatives of a function is the integral of the function with a variable bound of integration. 2. The integral of a function over some interval can be computed by using any one of its infinitely many antiderivatives. Put simply, the antiderivative of a function is equal to its area under the curve and vice versa.
Although calculus can find its roots in geometry, its applications reach far beyond that of finding areas under curves. Calculus can be used to create mathematical models in order to find an optimal solution. Physics integrates a lot of calculus into its concepts, such as motion, electricity, astronomy, and acoustics. Einstein's theory of relativity also uses calculus.
In the field of chemistry, calculus can be used to predict functions such as reaction rates and radioactive decay. Meanwhile, in biology, it is utilized to formulate rates such as birth and death rates. In economics, calculus is used to compute marginal cost and marginal revenue. In addition, it is used to check answers for different mathematical disciplines such as statistics, analytical geometry, and algebra.
Thank you for watching.